Hey folks, this is another edition of Flippin' Physics. What we're going to do today is using those kinematic problems, we're going to do what's the famous cop problem. Here's the police officer. He's hiding or she's hiding on her motorcycle behind a billboard. And you're driving by, listening to your tunes, totally, absolutely oblivious to what you're doing. You're speeding. You're going, let's say you're going 40 meters per second. So the speed of you is 40 meters per second. We'll call you the speeder. So the speed of the speeder. And here's the key. You're going at a constant 40 meters per second. And you're oblivious. You're not going to change that at all. But the minute you pass the billboard, this person has zero reaction time. This cop pulls out, like sees you coming, knows you're speeding. The minute you pass the cop takes off and starts chasing after you. And the cop has a constant acceleration. The acceleration of the cop is, well, first he's going from rest. So the initial speed of the cop equals 0. The acceleration of the cop is, let's make up some numbers. Let's say 4 meters per second squared. That means every second the cop is going, the cop goes 4 meters per second faster every second. Starts from rest. Okay? And the question is, at what time t does the cop catch up to the speeder? Okay? At what time t does the cop catch up to the speeder? And where down the road are you guys? How far from the billboard are you? We'll say X initial is the billboard and we're looking for X final. All right? So there's the question. What I want you to do, hopefully, you're going to pause this video and work that out and see what you get for an answer. So really, pause it. Because if you're just going to watch this video, you're like watching somebody play football, and you don't get any better doing that. So pause the video and try it now. All right, hopefully we're back, and you actually did try this thing, and you worked out what you got as an answer. Here is what a lot of newbies, a lot of rookies will do. They will say, he's accelerating at 4 meters per second to catch up to the speeder. The speeder's going 40 meters per second, so it takes 10 seconds for the cop to catch up to the speeder. 10 seconds is the wrong answer. It is not 10 seconds. Okay? So why isn't it 10 seconds? He caught up. He's going 40. 40, 40. But he's still 3 blocks behind. Just because the cop is going 40 doesn't mean the cop caught up to the speeder. The question is, when did the cop catch up to the speeder? That means same position. The cop going the same speed as you is not the answer to the question. When is the cop in the exact same position as you? When is the cop passing you? This is what the question is. So if you mess that up, pause the video and see if you can come up with a way of coming up with same distance, same time. Because that's what the question was asking, when you catch up to the speeder. Okay? So give that a try. Pause the video again and try it this time if you didn't do it before. Okay? If you got 10 seconds, you should be stopping the video right now and trying it over again. All right. Hopefully you're back and you actually got the right answer this time. Let's go through it and see if I can get the right answer. Hopefully I can. They give me lots of money for this course. What is the only equation we can use for the speeder? Hopefully you realized the only equation you use for the speeder, we'll use green for the speeder, all right? The only equation you can use for the speeder is equation A. And equation A states that V average equals change in displacement or distance over time. If it's a speed, then that's distance. And we're going in a straight line, so the magnitude of the displacement is the same as the distance. Okay? So that means x final equals x initial plus v average of the speeder times time. But did you notice I said that the speeder has a constant speed? So a constant speed means you don't have to worry about the word average. It's always 40. That's beautiful. The minute you hear constant speed, no acceleration, constant speed, no acceleration, equation A is the only equation you can use. So sometimes when you're new at this, you're like, oh, what equation do I use? What equation do I use? If there's no acceleration, there's no choice on the equation you're going to use. Equation A is the only one that makes any sense. Go through all 5 kinematic formulas. They all fall apart except for equation A. Okay? Equation A when you don't have A. When there's no acceleration, use equation A. So here goes. X final, where is the speeder? Equals 0, started at the billboard, plus 40 t, 40 meters per second t. So this is the equation for the speeder. Now, some of you new people going, I didn't know what to do because I have 2 unknowns. I didn't know what. Write it down. Just write the equation down. This is where with respect to when. You can't go any farther than that yet. But the question is, when does the speeder get caught? When does the cop catch up to the speeder? Okay? So that's the equation for the speeder. Can you think of an equation for the cop? Let me tell you again, with the cop, it started from rest, accelerated about at a constant 4 meters per second squared. And the question is, where's the cop with respect to time? So we got to find an equation that has to do with initial velocity, acceleration, displacement, and time. You thinking of the same equation I am? If you've done some of your homework, you know that that's equation D. X final equals x initial plus v initial of the cop times time plus 1/2 at squared for the cop. Okay? This is 0, and this is 0. So really the equation is x final for the cop equals 1/2 at squared. So for the cop, that's the equation. So now I have an equation for the speeder, and I have an equation for the cop, and the question was, when does the speeder get caught up by the cop? When does the cop pass the speeder? So that's when the speeder and the cop are in the exact same place at the exact same time. See, here's the answer to the thing. Set them equal to each other. The position of the speeder is the same as the position of the cop. Isn't that cool? So all you had to do is set those two equal to each other. X final for the cop equals x final for the speeder. So that means 40 t equals 1/2 at squared. Broke. One half at squared for the cop. Okay? One of the t's cancel, and you end up with 2 times 40 equals a, or 1/2 a equals 40. Solve for t. What's 1/2 of a? A was 4, 1/2 of a is 2. 40 divided by 2 is 20 seconds. So right here, 20 seconds is the time it took for the cop to catch up to the speeder. Where is the speeder at 20 seconds? X final for the speeder is 40 times 20 seconds. That equals 800 meters. Now let's go back for a minute. Remember where some of you might have put in 10 seconds by accident because you didn't really know what catch up means? Okay? Then that person was 400 meters away after 10 seconds. Now let's go over here. Over here it's 1/2 at squared. That's the position. So what's 1/2 times a times 20 seconds squared? 20 seconds squared is 400. Half of 400 is 200. 200 times 4 is 800. So the cop is 800 meters away from the origin, and so is the speeder. So that's when the cop is passing the speeder. Try it with 10 seconds, and you'll get 10 squared is 100, 400, half of 400 is only 200. So this is that whole thing about a parabola. That cop is undergoing parabolic motion in the sense with displacement, that cop is starting off slow and then picking up a whole lot more distance later on. So after 10 seconds, that cop is only 200 meters away from the billboard, and this guy is 400 meters away from the billboard. So the cop is actually only halfway to the destination at 10 seconds. So 10 seconds was definitely not the right answer. Now, can we graph something like this? Can you visualize this? Can you get it to a place where you actually see it going here? So what if we graphed displacement versus time and velocity versus time for the two cars? Okay? So green means go. So what does the motion of the speeder look like from rest? So it started from rest, and the speeder went at a constant slope of 40 meters per second. That's the slope of this line. Displacement versus time gives you speed. So this is the speed of the speeder, how fast the car's going. Okay? What does the cop's graph look like? Okay? It'd be awesome if you paused the video and thought about that. All right, hopefully you paused it and gave it a shot. This is what I think it looks like. The slope of the line in the beginning is 0 because the cop's not really moving. And then the cop's increasing speed, increasing speed, increasing speed, increasing speed. And so all you got to do is look at right around 10 seconds, and at 10 seconds they have the same slope. The slope of the line of this is 40, and the slope of the line of the cop at 10 seconds is 40. I didn't ask you that, but the cop's going 40 meters per second after 10 seconds, right? Changes by 4 every second for 10 seconds. So therefore, the cop's going 40 after 10 seconds. Who cares? That's not where he caught up. I'll show you where he catches up, right over here. He catches up at 20 seconds. That's how fast is he going? How fast is the cop going after 20 seconds? The answer to the question. So the speed of the cop at 20 seconds is equal to the initial speed of the cop, which is 0, plus AT. So at 20 seconds, it's 4 times 20, and the cop's going 80 meters per second. The cop actually is moving at twice the speed of the speeder when he passes him. The slope of this tangent line is twice 40. This is 80 at this. Right here, the slope of this line is 40, but the slope of the line over here is 80. Isn't that cool? You get a lot of stuff on that graph. Okay? All right, try velocity versus time. Do me a favor and pause the video and try that. All right, hopefully you're back and you didn't just pretend you did it. This one should look straight across because it's 40 the whole time. 40, 40, 40, 40. Every time you look, that speeder's going 40. But this person is changing their speed. They're starting from 0, and they're going like that. And the slope of this line is equal to, the acceleration, 4 meters per second squared, and the slope of this line is equal to 0 right there, 0 meters per second squared, because the slope of this line, velocity versus time, is acceleration. All right, so what you want to do is realize something really cool. This second graph gives you some great information. Check this out. If I find the area here, and this is 20 seconds, this area is 40 times 20, and that's 800. If I found the area of this triangle that the cop was making, that cop made a triangle that is 1/2 base times height. Remember how fast the cop was going? 80 at 20 seconds. The cop was going 80 meters per second, And so 80 times 20 times a half, because it's 1/2 base times height, is, I'll be surprised, 800 meters. So the cop and the person are going the same exact distance. Okay? All right. Now, if you were taking just the regular easy physics course, we would have stopped right there. But you guys are big and strong and smart. So why don't we just tweak it a little bit? Okay? Here's what I want you to do. Same question. Okay? So the cop is going, V initial equals 0 for the cop, and A for the cop equals 4 meters per second squared. Okay? And the billboard is still X initial equals 0. Okay? That's the cop. But what about the speeder? For the speeder, V is a constant, 40 meters per second. Okay? But this time, let's have the cop have a 2-second delay. Okay? So that means the speeder is driving past the cop, passes the billboard, and then keeps going, and the cop takes 2 seconds to drop the donut, start the car, and take off from rest. So the only difference here is there's 2-second delay for the cop. So what I want you to try to do now is to figure out, when did the cop catch up with the person, and how far down the road were they when the cop caught up with the person. Now there's a 2-second delay. There's a really easy way of doing this. Well, not that great easy, but there's a simple way, and then there's a really crazy hard way. So think about this. I'll give you a hint. Why don't you start your clock when the cop takes off? So where is everybody after 2 seconds? If we start our clock when the cop takes off, and then stop our clock when the cop catches up, then that would be the easiest way of doing it. Where's the cop at t equals 0? And where's the speeder at t equals 0? Okay? Pause the video and try that. All right, hopefully you are back 10 minutes later. And if you're not, you're just getting entertained by my video, but you're not learning anything. The struggle is what gets you fertile enough and ready enough for when I show this to you, you go, oh, I get it now. You got to struggle first, otherwise the stuff that doesn't seem to be retained. I don't know why it's like that, but it's not like that. You can't just sit and spectate. Stop the video and try it. Okay? So if you haven't done that, do that right now. All right, I'm going to do it the easy way. The easy way is this. If there's a 2-second delay, okay, then I'm going to start my clock at t equals 0, but where is the speeder? Where is the speeder located? What's X initial for the speeder? And the answer is, the speeder is, after 2 seconds, going 40 meters per second, 80 meters down the road. Okay? So if the speeder is 80 meters down the road, then you have an equation that's a quadratic. Let's set that bad boy up. The only equation here is x final equals x initial plus v average times t. That's for the speeder. So that means x final equals 80 plus 40t. You get me? That's the equation for the speeder. What's the equation for the cop? The equation for the cop was, let's go back down over here like this, that same exact equation as before, and that is x final for the cop equals x initial, but we're making the origin the billboard. X initial is the billboard, plus v initial of the cop times t, plus 1/2 at squared. But this is 0, and this is 0, so x of the cop, where is the cop, is equal to just 1/2 of 4, which is 2t squared. So the cop's equation is 2t squared equals x final. The green one is x final for the speeder equals 80 plus 40t. When does the cop catch up to him? When does the cop catch up to him? And the answer is when these two are in the same position at the same time. So you end up with 80 plus 40t equals 2t squared. If you move everybody over the other side, you end up with 2t squared minus 40t minus 80 equals 0. If you want to have some fun, you could take away the 2, and you got t squared minus 20t minus 40 equals 0. Now, can you think of two numbers multiplied together that give you 40? Multiplied together give you 40, but added together give you negative 20. What two numbers multiplied together give you 40, but added together it gives you negative 20? I don't know of one. So therefore, we have to use the quadratic equation. And the quadratic equation, you hopefully know, is minus b, which is a positive 20, plus or minus the square root of b squared, which is 400. Negative 20 squared is 400, minus 4 times a times c all over 2a. And that, folks, is the time it took for two things to be in the same place at the same time because of our conditions. Okay? So solve for that and give me the 2 times. There'll be 2 times, 2 roots. Solve for that and see what you get. Okay, we're back. And I tried the quadratic. I ended up getting 20 plus or minus. And then inside there, the square root stuff is 23.66419. If I add it and divide by 2, I end up with a positive time of 21.83. That's our answer, 21.83. And a negative root is negative 1.83 instead of 21.83, 1.83 negative. All right, so you throw out the negative root, and you get an answer of 21.83. Now think about this for a minute. He had a 2-second delay, which gave the speeder a 80-meter head start. So how long does it take for the cop to catch up to him now? Not 20 seconds, but a little more than 20 seconds. Almost 22 seconds. Okay? Not quite 22 seconds, though. It's really kind of neat how this works out. I want you to notice the other root. The other root is, instead of 21.83, it's 1.83 the other way. It's all kind of like hanging out near the 20 mark. All right? So you take that away from there, and you end up with that 20-second idea that we got from the other question. It's really kind of a neat concept here. If you graph this thing, you would really see how elegant this whole thing is and how the other root means something. Okay? So if we were going to graph distance versus time and velocity versus time, what would those graphs look like? Well, the cop and the speeder, this one's easy. This is 40 meters per second. And over here, it's just a flat line, 40 meters per second. That's the speeder, right? The slope of this line is velocity, and the velocity is 40. Okay? Over here, 40 shows up on the x-axis. Take the derivative of a constant, you end up with a flat line of 0. Okay? And what about that picture? Is it correct? Is it accurate? No, I forgot something. I probably should have put on here at t equals 0. At t equals 0, where is the speeder? The speeder is 80 meters away at t equals 0. When I start my clock, the speeder is already 80 meters away. Okay? And then the cop starts from rest over here at the real origin, right? And then accelerates, which means flat line in the beginning, and then a gradual increase in speed until they meet. Okay? And they're meeting over here at about 21.83 seconds. And somewhere over here, the cop is actually going 40. The slope of the tangent line for the cop would be 40. Okay? Over here, the cop is over here, and at t equals 0, cop starts from rest. And again, you get that graph where the slope of this line would be 4 meters per second squared, and the slope of this line is 0 because there's no acceleration for there. Isn't that kind of cool? Okay, so the cop catches up to him, but there's a little bit more. I just wanted to show you something kind of neat here, and that is this. If the cop was accelerating at 4, that means in the weird world of negative times, the cop would have been stopped at the origin, but the parabola would have continued here. And the parabola would have continued into the negative time zone. Guess what time that was when they were in the same place at the same time? It's not at the origin, it's not way far away, but it's right there. So at negative 1.83 seconds, they actually are in the same place at the same time. Isn't that kind of cool? I just like that. That's just really neat. Okay, so that's the cop problem. Hopefully that'll give you an idea of the level of questions that we ask in this class, because those are those 5 kinematic formulas you learned in high school, but now I'm stepping up it a little bit, and you got to actually get it to a point where you actually know how to do a little bit more complicated questions. I think you got some homework problems like this, maybe an Enterprise getting chased by a Klingon or something like silly with Starship Enterprise, but it's that same kind of concept. When are they in the same place at the same time? Like if a train is on the wrong track and they're going to collide with another train, how much do you have to hit the brakes so that they just bump? That means they're in the same place at the same time, but this time you would solve for the acceleration of the train to make that happen, okay? So give questions like that a try, and hopefully you understood a little bit of what I did and you're good at kinematics.